Okay, let's start today. Let's do chain rule. So let me remind you what we did. We have a function. So in general, I'll do this for two variables. The other variables you just keep adding. So suppose we have a function f of x, y. Okay. So we are interested in the cases when x and y are functions of some other variables. So in our case, suppose that x is a function of, okay, so let's say x of t, a function of t. Y is a function of t. Okay. So you read such things as a function of t. Okay, so how do you read this? This is x is a function of t. Okay, so this is what we mean when we write something on the left-hand side and something different on the right-hand side. Okay, then this makes z a function of t, and then it is natural to ask how fast this changes with respect to t. Of course, we will be interested mostly in the cases when all the involved functions are differentiable. But at this point, let us make the general definition. The question, the calculus question at this point, of course, is the derivative. Is how z changes. Let's say, emphasize that it's a function of t. How z of t changes as t changes. Okay, so this is asking the derivative of z with respect to t. Okay. Now this is the usual derivative. Now assume that all involved functions are differentiable. Then we have a special way of writing this definition. Otherwise, you just write the definition of the derivative. Here, you calculate z of t plus delta t minus z of t, divide with delta t, check if the limit exists as t goes to 0. That's the answer to this question, the derivative of z with respect to t if it exists. Now we are assuming that everything is differentiable, so those derivatives exist. In that case, we have a nice way of writing z, remember from last time. Using that, we will be able to give a nice formulation for the answer to this question. So this is how it works. So recall that if f x xy is differentiable, then we have the following thing. Differentiable, let us write it at a point so that the notation will be shorter. Differentiable at x sub 0, y sub 0. Okay. Then we have f of xy near x sub 0, y sub 0. This value can be recovered like this. Of course, first you obtain the value at this point. Then to obtain this, you move a little bit around. And if f is differentiable, we know exactly how to move around. You take the derivative of this with respect to x and multiply it with x minus x sub 0 plus the derivative x sub 0, y sub 0, y minus y sub 0. This part, remember, is the tangent plane. Okay? And then you have error term, epsilon 1 times x minus x sub 0 plus epsilon 2 times y minus y sub 0, where epsilon 1 and epsilon 2 are functions which go to 0 as this point goes to the center point. Okay? Now, in order to answer this thing, we'll rewrite this, introduce some notation maybe. You see, I'm trying to find the derivative of f with respect to t, so I have to look at this minus this and divide this by delta t. Okay, so this is what will happen. Let's say z prime t, and for this we have to assume that, so assume just for notation, x of 0 equals x of 0, y of 0 is y sub 0, just so that the notation will be nice. So the derivative of this at, say, t equals 0, at t equals 0 is f of x, y, or maybe I now start writing everything in terms of x of t. Okay, f of x of t, y of t minus f of x sub 0, y sub 0 corresponding to this. Then I divide it by t. Okay. So this is equal to, okay, now this side is, you see, this minus this. So I keep writing these things. So this is constant. Okay, so I leave it around back here, x sub 0, y sub 0, times I have x of t minus x of 0. Okay, x of 0 is x sub 0 divided by t, plus I write the other term, y of t minus y of 0 divided by t. I do the same with epsilon 1, x of 0 over t plus epsilon t, y of t minus y of 0 divided by t. Okay, so, well, here actually this is not equal to this, but this is going to be equal to the limit of this. Okay, so let me write it like this. Now, z prime of 0 is equal to limit as t goes to 0 of this expression. Okay, so let me just write this expression here, and we'll check if the derivative, if the limit exists. Minus f of x0, y0 over t. Okay, so here, of course, you see that in this part there is no information to calculate, but on this side, this expression is equal to this side, and on this side there is enough information to calculate the limit if it exists. Now we calculate the limit on this side. You see this is a constant, and on this part we assume that all these functions are differentiable, so this limit exists. This is the derivative of x at 0. This is the derivative of y at 0, and the same thing here. So these limits exist. Okay. So on the right-hand side, the limits exist, and we know exactly what the limits are. They are derivatives of x and y. So we write this as fx, x sub 0, y sub 0 times x prime 0 plus fy, x of 0, y of 0, y prime 0. Here you see now this is not a constant. I'm taking the limit of this product, which is equal to the product of the limits. The limit of this exists, which is 0. The limit of this exists, which is x prime. So 0 times x prime, 0. And the same thing here. Okay, so this is the part which makes differentiable functions useful. Okay, if this limit did not exist, then I would not be able to say anything. But fortunately, this limit exists. And again, fortunately, it is 0. So this part disappears. And the derivative of the composite function has a very nice expression. Okay, so this is the derivative at this point. At this point, notice that this is actually a dot product. So let me say, notice, we'll come to this. I have this vector, f x, x sub 0, y sub 0, f y, x sub 0, y sub 0, dot product, x prime 0, y prime 0. And notice again that this part is a geometric meaning. This is velocity vector t at 0 if the position vector is equal to x of t, y of t. Okay? We'll come to the meaning of this and consequences of this later today. But at this time, we just noticed that it is already here. But at this moment, we are interested in this equality. The partial derivatives act like this to give the derivative of the composite function. There are several ways to write this, because in solving problems, we immediately want to write down the formula. Okay, so for example, this one is, since this depends only on one parameter, I say derivative of z with respect to t. Remember that derivative is equal to this, so maybe I write it to show how we are writing this, f of x, y. Okay, derivative of this with respect to t is equal to derivative of this with respect to the first variable times the derivative of the first variable, plus the same thing with the second, plus if we have 35 more derivatives, you keep adding the same thing. The derivative of this with respect to this variable times the derivative of this variable, plus you continue. Okay, so this is now partial derivative of f with respect to x. Okay, so when you are taking this derivative, you write this without considering the dependence of x on t. Okay, f of xy is a formula. You take the derivative of this with respect to x. That comes here. Okay, and then you multiply it with the derivative of x with respect to t. Derivative of x with respect to t. Okay, here I'm paying attention whether it will be curly d or straight d, but in practice it doesn't matter. Okay, only if you are in a very polite society, they want you to obey to those rules, but in practice, of course, you are just talking about derivative with respect to a variable. It doesn't matter whether you use curly or other thing. So plus, I have one more variable here, so this is derivative of f with respect to y times derivative of y with respect to t. Okay, so this is the general formula. You notice that here I didn't I didn't evaluate these things. So if we are going to do this, you evaluate this, you evaluate this all at t equals 0. Okay, if z prime t sub 0 is required, you calculate the right-hand side at t equals t sub 0. So this requires x to be calculated at x t sub 0 and y calculated at y t sub 0. Okay, so that's probably the only thing where you have to be careful in doing chain rule. Also in one variable. Okay, you take the derivative of this function and then you take the derivative of the variable, you multiply them. But now if you want a number, you have to evaluate them at the correct way. Okay, so you evaluate them at the values specified by the final parameter. When t equals t sub 0, okay, so it is easy to see, since x is given as a function of t, it is easy to see where to evaluate this. You just put t equals t sub 0. But where you come here, this is a function of x and y. Okay, so each x and each y takes a certain value at t equals t sub 0. So you take those values of x and y and you put them here. So this is the only thing to be careful about. You also write this as derivative of z with respect to t is derivative of z with respect to x times x with respect to t plus z y y t. Okay, so when you write it this way, it is also easy to remember what is happening. So when you write it this way, then you are not tempted to cancel these. Okay, so this tells you that they don't cancel. If we had only one variable, remember that if you have one variable, if you cancel these dx's, you still get the correct answer. But that only works in one variable. Okay, now that we have this, we say what happens if x and y depend not only on t, but on several variables themselves. Okay, suddenly we think that we face a totally different problem, but after a second of panicking, we realize that if you have 10 more variables there, when you are taking derivative with respect to t, you keep all the other things constant. Well, this is also what you did here. You only consider t as a variable. Whatever you see besides t, we were expecting to see only numbers here, but whatever you see, even if they are not numbered, they will be constant. So it doesn't matter if x depends on 5 more variables. Okay? Only the notation changes a little bit. Okay? Okay. let's say, what if x is a function of t and s, and y is a function of t and s, okay? So since derivative of x with respect to t means keep all other variables as constant, nothing changes in the previous arguments of chain rule. Okay? Maybe if you just want to be aesthetic about this, this notation will change because now x is a function of t and s, so I'm talking about partial derivative of x rather than just the straight derivative of x. But that's not a major problem. I can write it like this. So, okay, z is equal to f of x, y, and I have these. So partial derivative, okay, now z depends on, now z is a function of t and s, okay? So partial derivative of z with respect to t is equal to partial derivative of f with respect to x times partial derivative of x with respect to t plus partial derivative of f with respect to y, partial derivative of y with respect to t. Okay, so you see, once you do the main argument here, this is the crucial argument that we have, and this follows from assuming that f is differentiable, and f is differentiable is a concept that we invented artificially because all the nice functions we have exhibit a tangent plane around every point. Okay, so, and this tangent point nicely approximates the function from our previous experience of curves. Okay, so we just interpreted this intuitive expectation, and we said that nice functions, in our mind, the picture is that it is nicely curved and there is a tangent plane. Now, if you want to express this algebraically, it will be like this. Differentiable function, this thing will be written like this. It will be approximated by the tangent plane, and it will be an error which goes to 0 very fast. This is the algebraic part, but what we have in mind is a nice tangent plane. So all these complicated things, complicated looking things, arise from our experience of visual surfaces in R3. We just write the algebra for that, and then we realize that this algebra works in every dimension. Okay, so sometimes this dependence is not symmetric like this, that it may be complicated. Then we need to draw a dependence table. So dependence tables is a nice game which is endless source of midterm and quiz questions. Okay. So in general means that now that we understand the theory totally, we start playing with it. Okay, we create artificial problems. In general, x and y may depend on several variables, but not all at the same time. Now, what that means is the following thing. Okay, so we have this function z, which depends on x and y, okay? But z depends, say, on x and y. In this notation, whatever you see here depends on all the things below if it is connected by a path like this. So x depends, say, x depends on t and s at all. And suppose y depends only on s. So this is an example. Okay. So for example, does z depend on t? Yes, because there's a path going from here. Does that z depends on s? Yes, because there are even two paths going there. Y depends on s, but y does not depend on t because there is no path. In our game here, we are only following paths downward. So this is not, in our definition, in our game, this is not a path. So you only go down. There's no way to go from y to t by just following arrows down. So y does not depend on t. Okay? So here we read this. So I'll write this only once, because then after that we'll just understand it. So this part means z depends on x and y. And here x depends on t and s. Y depends on s alone. Okay? Since z depends on x and y, and they depend on this, z depends on t and s. Okay? Now we can write the chain rule by looking at this. Derivative of z with respect to t is equal to, now you follow all possible paths going from z to t, and for each of them you interpret as follows. This arrow here, okay, you don't write this, but in your mind, this part is, this path reads as z, derivative of z with respect to x. This path is derivative of z with respect to y. So this part is, in this case, derivative of x with respect to t. This part is derivative of x with respect to s. This is derivative of y with respect to s. Okay, so you don't write those things in your mind because it's obvious and you are going to write them here anyway. Now, following this, you multiply everything you see along the way, plus then you go and find another path, and again you follow that path up to here, and you multiply everything you see along the way. When you are finished, that's the derivative of this with respect to that variable. So in this case, you see there is only one path going here. So derivative, I see this on the path, derivative of z with respect to x times derivative of x with respect to t, plus there is no path, so I stop here. Now what about the derivative of z with respect to s? There are two paths, okay? So there will be two summands. First, I see these on the path, I multiply them. Derivative of z with respect to x times the, derivative of x with respect to s. Okay, so these things can be curly. Plus, the other path is this one, and I see this on the way, derivative of z with respect to y times derivative of y. Okay, again, I'm mixing straight and curly brackets, these. Okay, so this is the partial derivative of z with respect to s, which is in general easier to write because you are not using your brain anymore. You use your brain to derive this formula, to derive this game. Once you know the rules of the game, then you keep playing. Okay, so you see that this is now a very nice source of inventing quiz questions. So let us invent a quiz question for us, and then get 100 out of 100 from that quiz. Okay, so suppose now a nice quiz question. Okay, so z is a function of, say, x, y, and, okay, let's say w. Okay, x is a function of s and t. Okay, let's say there is another variable. Somehow x doesn't like it. Okay, y depends on s and r. W just depends on t. Okay, we are inventing these things, and there are two more variables, u and v. R depends on v, t depends on both of them. Just to make life complicated, s depends only on v. Okay, so this is how you prepare quiz questions. So you just arbitrarily write them. Okay, now obviously z is a function of u and v. Since this is a calculus topic, the question is what's the derivative of z with respect to its variables. Okay, so the question is what is derivative of z with respect to u. Okay, so the same rule applies. We follow all paths from z to u, and along each path we multiply whatever we see on the arrows. Arrows are going downward, and then we add all such possible paths. Okay, let's see. We have one this once we go to S, we will not go to there. So first, when you go to S, you go to T, and you go to here. Okay, so this is one path. So let us write it. Derivative of Z respect to X, I see here. Derivative of X respect to T, and derivative of T with respect to U. Okay, so this is one path. I found this one. So there is no other way to go U from X. So X is complete. Now I go to Y. Okay, so if I go like this, I don't see U. If I go like this, I don't see U. Okay, so this one will not contribute. I come to this one. I go like this, and I reach U. So that's one path. So plus derivative, I see this one. This one is derivative of Z with respect to W. Derivative of Z with respect to W. This one is derivative of W with respect to T. And this is derivative of T with respect to U. Okay. So there is no other path. So if I want to write now derivative with respect to B, you see we'll have lots of other choices. Derivative of Z with respect to B. So again, let's play the game. This one is one path, so let us write that. Derivative of Z with respect to X, X respect to S, and S V plus, okay, so from X I went to S. I can also go to T, and then I'll have this. So now I write this thing. Zx times xt tv plus, okay, so let's look at y. I can go to y, and then from y to r and s, both of them go here. So, okay, I'll write it. Plus z y, ys, sv, plus I again go to y, zy, yr, and rv, plus, okay, so there's no other way to go from y to b. I go to w. From w, I can go to t and v, and this is the only way. So this one reads zw times wt times tv. Okay, so this is the derivative.
Does it take only one leaf nodes?
For?
Leaf nodes,
Which nodes?
leaf, the bottom.
The bottom? Yeah, here.
Can you use this technique for like T?
Well, now here S, T, and R are functions of U and V, and the dependence is this.
Yes. Can you use this technique for calculating the partial derivative respecting to S?
Yeah, yes, certainly. If you stop seeing, if you don't want to consider the dependence of S, T, and R on U and V, you can stop here, and now you can write the derivative of Z with respect to S. Okay, so some of you just will stop at the right points. Okay, so you just write the same thing. You ignore this part of the diagram, and you just write the derivative with respect to S, T, and R. It is also possible that these guys depend on some other parameters, but in this particular example, we ignored that, so you can see the picture like that. Okay. So I'm not saying that one method is more advantageous than the other. It always depends on the problem at hand. That's why in science you have different techniques, and there are overlaps of these techniques. So some problems can be solved both by this technique and the other. You just decide on the problem, depending on the problem, which one will be easier. Okay. So this is what we want about chain rule. So in 5 minutes, we'll have a surprise quiz about chain rule. So another quiz question for these things is, you see, okay, so this is too complicated, but again, we can give you these numbers. Suppose I give you all these numbers, okay, in a table, and I ask you to find this. So what you'll do is you'll write this and plug in the values. Okay, but it will be an easy quiz. To make it a very difficult quiz, I'll give you also lots of other redundant information. Okay, so I'll give the value of this at v equals 0. Then I'll also give the value of this at 35, at 72. I'll give all numbers related to the values of these functions that evaluated at several unrelated points, and among these you have to choose the correct points. Okay, the correct points will be chosen according to this. You see here I am evaluating t at the correct point. In this case, t is evaluated at 0. Okay, so y should be evaluated at 0, and if something depends on y, it should be evaluated at the value of y at 0. Okay, so that's the only thing to keep in mind. So you don't just plug in numbers. So let me give one example like this, and then we'll have the quiz. The quiz will be about something else. So let me check so that I'm not lying to you. If I remember, it was about chain rule. Yeah, okay, a function is given. Yeah, you'll do chain rule. Okay, so there is a cooked up example, so I'll copy it from the paper. Every time I copy something from the paper, I make a mistake. So be careful what I'm writing. It's your responsibility. Okay? So in front of the cameras, I'm declaring that anything I write wrong, I'm writing it deliberately to check if you are sleeping or not. Okay? So that relieves me from all responsibility. We have z, a function of x and y. Okay? And apparently here x is given by a function g of t, and y is given as a function h of t. And now the given values are like this. F of x1, 2 is equal to 3. F of y1, 1, 2 is equal to -7. And g of 4 is 1. H of 4 is 2. G prime 4 is 11. H prime 4 is 5. Okay, so these are going to be the relevant numbers. Obviously, then in the quiz, you'll be given fx 3, 5 is equal to 35. Fy 3, 5 is equal to 71. G1 is equal to 4. H2 is equal to 44. G prime 1 is equal to, maybe not to make you suspicious, I should make all of these ones. G prime 1 is 23. H prime of 1 is 58. Okay, maybe some other numbers. Of course, we put these numbers a bit more carefully because this number should look like this number should look like this number. Okay, so if you are not careful, you will get confused. But if you know what you are doing, you'll just write the derivative of this. And the question is find. Okay, so the question will be like this. Let phi of t be f of g of t, h of t. This is t. And the question is find phi prime at 4, I think. It's probably, yeah. Find phi prime 4. Okay, so we carefully managed to make everything look different than chain rule. Okay, because we have a function of a single variable, find the derivative of it at 4. Okay, but now the solution is easy. You will not hesitate a second. You'll write the. Okay, so let me use purple. Okay, so since phi is equal to this is a function of two variables. Each variable depends on something else. Okay, so obviously this is a chain rule. So phi prime of t is equal to derivative of x at, now you have to write this carefully, not to confuse. After a while, you don't write these things. You know in your mind that you'll evaluate at the right point, but now I'm writing it deliberately like long term like this to see that we'll put t equals 4, then t equals 4 goes here, and g takes care of it. Okay, this times derivative of this, okay, it is g, so g prime t, plus derivative of f with respect to y evaluated at g of t, h of t, times derivative of what I see here, it is h prime t. Okay, so what was the question? In this expression, put t equals 4. Okay, so again, since this is just a demonstration, I'll rewrite the whole thing. Okay, g of 4, h of 4 times g prime 4 plus fy g of 4, h of 4 times h prime 4. Okay. So normally you just write this f derivative f with respect to x times g prime fy times h prime, and in your mind you know that the numbers should be evaluated there. So this generally flashes through your mind in a second. You don't need to write it, but just as a demonstration I'm writing it. Okay, now the next step is to use the table. Now we use the table. You see, first I need to find g4 and h4. That's where I'll evaluate this function. So in this table, I see that they are given here. Okay, so this is fx 1, 2 times g prime 4. Is it given? It's given 11 plus fy 1, 2, because this is the same point. I check h prime 4. H prime 4 is given. It's 5. Okay, so in the table, lots of h primes will be given, evaluated at different points, but here we know that we need h prime 4, so you just check and find it like this. So next, I put these numbers in. I could have put those numbers immediately here, but you see this is just our first example. So I try to find the value of the derivative of f with respect to x at this point. In the table, it will be given at different points, but I see it's given somewhere here. Okay, so it's 3. So 3 times 11 plus 5 times, I find this. It is here, minus 7. Okay, so let me write in correct order. Minus 7 times 5. Okay, so if my old calculator did this correctly, the answer is 2. Minus 2. It's minus 2. Okay, so this is zaman geldi. Okay, so now surprise, we'll have a quiz. Okay, so the quiz about these chain rules, and it's again about this thing. I think I'm not giving you any numbers. You have to calculate the numbers, but you have to pay attention where you are evaluating the functions. Okay, so that's the purpose of the quiz.